So last class we do many exercises and we apply the Bernoulli equation to compute the velocity of the flow field. And then this is the slide the final slide in last week, and we stop here and because we changed the different flow conditions. Right now, I'm wondering to introduce how can we describe the rotational motion of the flow fluid. Okay, and as I mentioned in last week, we can describe the theta angle change at the different time point. Okay, so that's the main idea is how can we compute the theta angle at the different time. So in that case, as you can see, the theta we highlight here, which is an angle between the bisectors and the horizontal lines. And for these conditions, we discuss with the Coulter flow. So we can see at the time T1 and at the time T2, the theta angle are different. So we can say for a Coulter flow, which is the rotational flow. So the idea, we should define the theta angle first, and we try to observe the theta angle changes at the different time points, and then we can identify the flow is rotational flow or not. So the following slide, I'm wondering to teach you how can we compute the theta angle change with the time. So the idea we call that is the theta rate. So if we can compute the theta rate, and then we can identify the flow is rotational or not. Okay, so you can see the slide showing here, we have the figures, and we actually know the theta A in here, and another side, we have the theta B in there. And our theta defined by these figures in here. So the theta angle is the bisectors, the angle between the bisector and horizontal line, x-axis. So this slide, I'm wondering to teach you how can we define the theta angle, just based on the idea as the figure showing here. So the first we can identify, we start from the beta angle. So we have the beta. The beta angle in here will equal to, as you can see, this is 90 degree, right? Here is a 90 degree, and we write the 90 degree to be the radius unit. So we know that is 2 over pi, because the pi is equal to the 180 degree. So the 2 over pi is equal to the 90 degree. And then we know that the 90 degree, if we minus the theta A in here, so we can first, we minus the theta A. Okay? If the 90 degree minus the theta A, we will have the angle in here, right? The 90 degree minus the theta A, so we have a radial angle in there. And if we plus additional theta B, so we can have another angle in here is the theta B. So that the beta will equal to 90 degree minus the theta A plus the theta B. So we have the beta angle. And what is the bisectors in here? The bisector should be the 2 over beta, right? So we need to compute the 2 beta over 2. Because the half of the beta angle is, we can draw the bisector line. So that's why we draw the bisector line in here, just based on we wondering to divided the beta angle to the half the beta. Okay, so we have the bisector line divided by the beta over 2. Okay, so we know that the beta over 2 will equal to the 4 over pi and the minus the theta A divided 2 and the plus the theta B also divided the 2. Okay, but our final purpose is we wondering to define how the theta angle in here. Okay, so if you can identify from the figures, you know that okay, because we know that the theta will equal to the 2 over beta. Because right now we have a 2 over beta, okay? So we actually know the line angle in here. This is a 2 over beta. So I just write the number here. It's a beta over 2. And the beta over 2, if I plus the theta A. So that reason why I plus theta A, so I plus here. So that will equal to the theta angle. Okay, so the first idea, we first calculate the bisector angle, the beta over 2. And if the bisector angle plus the theta A here, and will equal to the total theta angle. Okay, so in here, we know that the theta is equal to the beta over 2 plus the theta A. So just write down the beta over 2 is equal to the pi over 4 and the minus the theta A over 2 and the plus the theta B over 2 and we have additional theta A angle here. Okay, so we can reorganize the equations. We put all the theta angle the same together. So the 4 over pi, I keep this degree, and the minus theta A over 2 plus the theta A will equal to the plus the theta A over 2, and we just write down the theta B over 2 here. Okay, so right now we have the theta angle can be defined as the pi over 4 plus the theta A over 2 and the plus the theta B over 2. But it's not our final purpose because we wondering to compute the theta rate. So right now we have the theta. So if we should compute how to change it with the theta angle at a different time. So how can we compute the theta rate? We just assume we have the delta t time difference. We have the delta t time difference. So all the parameter we should divided the delta t. But as we know, the 4 over pi is the constant value, didn't change with the time difference. So there is nothing, the pi over 4 cannot be changed with a different time. So in there, we can rewrite the equation to the 1 over 2, and because the theta A divided the delta t plus the 1 over 2 and the theta B divided the delta t. So we can rewrite it will equal to 1 over 2 and the theta A rate plus the 1 over 2 and the theta B rate, right? So that's the reason why we write down the equation here. We actually know the theta rate is equal to the half of the theta A rate plus the theta B rate. Okay, and I emphasize the conditions if the theta rate is equal 0, and then we can call that the flow is a rotational flow. Okay, so the idea is if we can compute the theta rate, and then we can identify the flow is rotational or not. Okay, so that's the next questions. How can we compute the theta A rate and the theta B rate? If we can compute, so we can know the values of the theta rate, and we can identify the flow is rotational or not. Okay, so the next slide, we're wondering to compute the theta A rate and the theta B rate individually, and then finally we can know how large the theta rate we have. Okay, so this is a little bit complicated, but you can see the condition is we have the point 0 here, and we have the velocity. Okay, we have the velocity u velocity along the x directions at the point 0 here, and we have the v velocity along the y-axis at the point 0 here. Okay, and then we assume there is the delta x changes, and there is the delta y changes. Okay, so that delta x changes, we move the point to the 1, and for the delta y changes, we move the point to the point 2 here. Okay, so we have the delta x and the delta y shiftings. Okay, so and we define the theta angle here is the theta A. Okay, here is the theta A, and we define another theta angle here, and we call that is minus the theta B. Minus the theta B. So how the difference? As you can see by your right hand, you can call the theta A. The theta A, the direction rotated is the counterclockwise rotate. So you by your right hand, the sign is the positive rotation angle. But if you see the theta B, the rotate direction is the clockwise. So the clockwise, you by your right hand, the rotation angle is the minus. So that's why there is the positive theta A, but there is the negative theta B, because the rotation direction is different. Theta A is counterclockwise, so the positive rotations, and the theta P is the clockwise rotate. So the theta angle is the minus. So the idea is we first focus on the theta A. So I write down, if I focus on the theta A, so the first I wondering to know the theta A, how large it is. Okay, and then we can see if I define the theta A angle. Okay, here the theta A is the delta theta A. I just write down the theta A. So if you focus here, what is the sine theta A? So we have the delta x here. Okay, and we have the delta y1 here. Okay, so we know that what is the sine theta A? The sine theta A will equal to the delta x over delta y1, right? Because it's just based on the geometries in here, you know that there is the delta y1, and the line in here is the delta x, and the angle here is the theta A. So we know that the sine theta A is equal to the delta y1 over delta x. So the idea is, how can we compute the delta y1? If we can compute the delta y1, we can compute the sine theta A. Okay, so we don't know the delta y1. What's the values? Okay, so we go back to see here. We have the point 1 here, and we wondering to know what's the point 1 velocity. So I pick the point 1 in here, and what the velocity along the y-axis. This is our point 1, the point 1 in here. Okay, so I assume the point 1, the velocity is the v. Okay, initially the velocity y-axis is the v, and I plus the dv dx multiply the delta x. So this is the velocity at the point 1 is the v plus the dv dx multiply delta x. I assume the point start from the 0 to going to the 1 point here. The v velocity will change, and the change is depend on the linear velocity gradient and multiply the delta x changes. Okay, why I multiply the delta x? Because the changes, the difference distance is the delta x here. Okay, and I assume there is a linear velocity gradient from the 0 to the point 1. So this item dv dx, I assume the velocity changes is a linear velocity changes along the x directions. Okay, so dv dx is a linear slope, and I multiply the spatial changes is the delta x. So this is our new velocity at the point 1. So I wondering to compute the delta y1. So what is the delta y1? The delta y1 will equal to the velocity at the point 1. Okay, this is the velocity at the point 1, and then multiply the delta t changes. So this is the travel distance along the is a point 1 move to the point 1 prime here. This is the travel distance is the 1 move to the 1 prime. The point 1 to the 1 prime. So this is the total travel difference in here. Okay, so this is the travel distance. And if I keep the velocity at the point 1, what the travel distance is here is a v multiply the delta x. If I keep the velocity at the point 0, and the velocity is always the v, so the distance I need to minus the v multiply the delta t changes. So this is the difference between two travel lengths is equal to the delta y1. Okay, so I can compute the delta y1 here. So you can expand reorganize the final result, and we only have the dv dx and the delta t multiply the delta t, right? Delta x multiply the delta t. So this is our delta y1. So we go back to define how large the theta a sine is the dv dx delta x delta t divided the delta x. Okay, so you know that the sine theta finally will equal to the dv dx and multiply the delta t. Okay, and sometimes we assume the theta a in here is quite smaller. So we assume the theta a is very small. Okay, so that we can say that the sine theta a will equal to the theta a. If the theta angle is smaller, we can say that the sine theta a is equal to the theta a. Okay, and then we know that the theta a will equal to dv dx and the delta t, right? And we're wondering to compute the theta angle, okay, the rate. So we know that the theta a rate will equal to the theta a divided the delta t, right? Because we're wondering to compute the rate. So finally, we know that the theta a rate will equal to a dv dx. Okay, so this is our first theta A rate is equal to the dv dx. Okay, so the similar ideas we wondering to compute how about the theta B. So how about the theta B? So we can also similar, we pick up the point in here. So we know that we have the point 2. This is the point 2. And we also know that the point 2, the velocity, I can rewrite the point 2 velocity along the x direction u. And I assume the linear velocity gradient increase. So the du and along the dy, the y changes and multiply the delta y. Okay, this is the velocity of the point 2 is going to the right. Is u plus the du dy multiply the delta y. Why we multiply the delta y? Because the location changes is the delta y. Okay, so I assume the velocity is also changing. Okay, and then similar, we can write down the equation. What is the sine theta b? So we have the theta b here, and you can have the length is the delta y, and the b, the sine theta b, will first us to the delta x2. So we can write down the equation is the delta y over delta x2 is the sine theta b. Is the sine theta b. So similar, we don't know the theta delta x2 how large it is. So again, we can compute the travel distance in here. Okay, this is the travel distance as the location 2. And we have additional travel distance is a u multiply delta t here. So we actually know what is the delta x2 is equal to the u velocity plus the du dy delta y multiply the time changes. So this is the travel distance for the point 2, and minus the u delta t. So I just pick up the distance here minus the distance in here. And then that will equal to a delta x2. Okay, so the result here, we only have a du dy and delta y multiply delta t. Okay, so we put back the number, go back to define the sine theta b. So the sine theta b is equal to the delta x2 divided the delta y. So the sine theta b, finally, we only have a du dy. Sorry, so here I need to keep the absolute, the sine theta b, because we know that the sine theta b is the minus. So I don't want to change the sign result, so I use the absolute angle here. I use the absolute angle here. And I know that they will equal to the delta t. And again, I also assume the sine theta b is quite smaller. Okay? So finally, I know that the sine absolute theta b will equal to the absolute theta b, and it will equal to the du dy delta t. And finally, I know that the sine b rate, and here I don't use the absolute because I actually know the sine theta angle is the minus. So I have an additional minus here, and that will du dy. Okay, so this is our another answers. So why the delta t disappear because we compute the theta rate, so we also divided the delta t here, and then so we can cancel out the delta t here. So we know that the sine theta rate b is equal to the minus du dy. So why the minus? Because we know that the rotational angle for the sine theta b is the minus, is a negative sign. So that's an additional minus here. Okay, so we can go back to define. Previous slide tells us the theta rate will equal to the 1/2 the theta A rate plus the theta B rate, right? So we just put the theta A here, rate, and the theta B rate here. So we can rewrite the equation to be the theta A is the dV dx, and the theta B rate is the minus du dy. Okay, so and because this is the rotational angle rate is along the z directions, so usually we also will write down the z, because this is rotating axis is z and z axis, so we use the theta z rate will equal to the 1/2 dV dx minus the du dy. Okay, so in the features, if we know the velocity field, we have the u and we have the v velocity functions, and we can compute the theta rate changes very quickly just based on the equation showing here. And in that case, if we change the different rotating axes, so we will have the different theta rate for different rotation axes. Okay, so the next slide just summarize all the rotation axis results. Okay, so as you can see, the first one is previous slide we derive the theta rate along the rotating axis is the z. Okay, and the second, if we change the rotation axis to be the x directions, and we can rewrite the theta rate will equal to the d omega dw dy minus the dv dz. And if we change the rotation axis is the y along the y directions, and the rotating rate will equal to the du dz minus the dw dx. So actually, it's very difficult to remember. So I wondering to tell you, the finally, if we wondering to define the rotation angle, that will equal to the spatial gradient operator cross product with the velocity field. Okay, it will similar to we have a different rotation axis, and it's quite equal to the spatial gradient cross the velocity factors. Okay, and in the next slide, I will show why we use the cross operators, and we can define the rotation rate. Okay, and sometimes because we mention the flow is rotational flow, that will indicate the flow problems will involve the viscosity effect. So sometimes we call the ideal flow, we will say that the flow is irrotational. The irrotational is similar, we say that the inviscid flow. Because the rotational flow, the viscosity effect will involve in our problem. But if we actually know the flow is irrotational flow, that means the viscosity effect is not important in our flow. Okay, and similar, we always say that the flow is incompressible, right? So it's sometimes we call the ideal flow, we will say that it is the irrotational and the incompressible. Okay, So that's a definition for the ideal flow. So the next slide, we will define one important parameters. We call that the vorticity, 波度. Okay, and you can see the vorticity will equal to, usually we call that the vorticity, use the omega, and the omega will equal to the spatial gradient cross with the velocity factors. And why? The reason there is 2 times. There is 2 times because in previous slide you can see we always have the 1/2. Okay, so that's why there is 2 times. Sigma is indicated. We wondering to normalize the constant factor, constant values 1/2 to be the 1. Okay, so in the features, if we wondering to identify the flow is rotational or not, you can directly compute the cross, gradient cross with the velocity factor. And then you can say is equal to the 0 or not equal to 0. If the vorticity is equal to 0, and then you can conclude the flow is irrotational flow. Okay? If not equal to 0, you can say that the flow is rotational flow. So it's fine if you cannot really follow me for the previous slide why we compute the theta rate. Okay? But you need to remember the final. When you would like to identify the flow is rotational or not, you should compute the gradient operator cross with the velocity factor. And you just figure out the result is 0 or not. And then you can say the flow is rotational or irrotational flow. Okay, so it's just based on the idea for the formula showing here. Okay, so it's a very important. When we see the flow, and we know that the flow velocity, okay, as the exercise showing here, we have the velocity factors is equal to 10 times x, and along the x directions, I, and minus the 10 times y, and the direction is along the y axis. And we call that is 2D flow field. Okay, so we don't have the z dimensions. And then we wondering to answer is the flow irrotational. Okay, so we already have the velocity function here, so we can do very quickly. We know that we can define a vorticity, right? So we have a vorticity omega is equal to the spatial operator cross with the velocity factor. Okay, and then we know that how can we define the cross? So we have the I and J and K, right? Even though we know that the flow is 3-dimensional, it's 2-dimensional, but we still compute the cross product. And then we know that here is the dx and the dy and the d and dz, and we have the u, v, w velocity, right? And if we compute our rotational angle is along the I directions, and we know that the inside here, so we can do the I directions. So we only compute the 2 operators is the dw, dy, and minus the dv, dz, right? And if we consider our rotational angle is along the z directions, okay, and we can consider, okay, along the z direction, so we can compute the the operator, we only have the du, dz, and the minus the dw, dx. So finally, we only focus on the rotational angle is along the z directions. So again, we consider a k direction, so we only compute the two operator is the dv dx minus the du dy, right? Okay, so now you actually know the velocity u is equal to the 10x, right? And the velocity v is the minus 10y. And we don't have the w velocity is 0. Okay, so you can put all the u, v, w inside the equations. Okay, so we can see the vorticity omega, and we do the cross operator, and we focus the I component. And you see here, we don't have the w, right? So we don't have this item. And the dv, the v is not a function of the z, because the v is only a function of the y. So we don't have this item. So for the I directions, there is 0, right? We don't have any others values. Okay, so we move to the z directions. And again, we can see that we have the u and the dz. But the u is only a function of the x. So we don't have these items. And we don't have the w. So for the z directions, we also have the result is 0. We don't have any result. And for the final, the k directions, dv, dx, but the v is a function of the y. So we also, this item is equal to 0. And then finally, it's minus du dy, but the u is only a function of the x. So we still don't have this item values. So finally, totally, the result is all equal to 0. So the vorticity, I can make the comment is 0. So the flow is irrotational flow. Okay, so the idea is very simple. You just identify the vorticity, and then you need what you need. You need the velocity field, and then you can compute the cross. Okay, the spatial gradient cross with the velocity factors, and then you can see the final answer is 0. So you can conclude that the flow is irrotational flow. So if you cannot understand the previous slide, I teach you how to derive the theta rate. Okay, but you can keep in mind the final formula vorticity here is equal to the spatial gradient cross with the velocity factors. And you can identify the final result is 0 or not to comment the flow is rotational or not rotational. Okay, so this is a very important exercise. So that's why I stayed here for a long time. And then the second exercise also we have the rotational problems. Okay, so in that case, as I mentioned, this is a Coulter flow. If you remember, the Coulter flow is always the rotational flow. And when we say the Coulter flow, that may the viscosity effect is important for the Coulter flow. That's the reason why it is the rotational flow. Okay, so what's the problem? The problem is we need to find the rotation angles, and at the locations with the 0.5 centimeter. And at this location, the fluid particle already travel the distance is 1 centimeter. Okay, so our major question is, if I pick out the 1 point here, and the location is the 0.5 centimeters. This is our point. And I didn't know the rotation angles. Okay, I wanted to know the rotation angle here. And my question is, initially the point in here. This is initially the point in here. And when the point travel the 1 centimeter distance, and how large the angle rotate. So initially this is our maybe T0, and after the T1 time, the point move to the right. When the point move 1 centimeter to right, and how changes of the theta angle. How changes of the theta angle rotate. Okay, so we have the theta we need to answer. And we actually know if we can compute the theta rate. Okay, if we know that the theta rate, and if the theta rate multiply the delta t time difference, and we can know how large the theta angle we have. So the key knowledge is we wanting to compute the first. We should compute the theta rate, right? And we know actually the dimensional in here, this is along the x directions, and this is along the y directions. Okay, so the theta rate we should focus on. The rotating axis is the z-axis, because we only have a Coulter flow is a two-dimensional flow. Okay, and as we know, the previous slide tells us the theta rate for the rotating axis is along the z directions is 1/2, and the inside is the dv dx, right? And minus the du dy. Okay, and then in that the Coulter flow, we don't have the velocity for the u directions. So in that case, we only have the 1/2 minus the du dy. Okay, we only consider this item because we have the velocity u directions. Okay, this is the u directions, but as you can see, along the different y directions, the velocity will change. Okay, velocity will change. So we actually know that du dy should be also the linear slope. Okay. So right now we know that we need to compute the u velocity as function of the y first. Okay. And you see on the bottom, the velocity here, u is equal to 0. And on the top here, the u is equal to the 2 centimeter per second. Okay? And how the delta y changes is the 1 centimeters from the bottom to the top. So we know that the gradient, the delta u changes with the delta y. The gradient we know actually is equal to the delta u is the 2 centimeter per second. Because the bottom, the velocity at the bottom is 0. And the delta y is the 1 centimeters. Okay? And we know that this is, if we multiply the y functions, and this is our u functions. The u velocity will increase when the y increases, right? The u velocity will increase when y increase. Okay, if the y is equal to 0, that means the location is on the bottom. The bottom, there is no velocity. Okay, so we can define the velocity as function of the y will equal to the 2 y is 2 times of the y, because the delta u is 2 centimeter per second, and the delta y is 1 centimeter. Okay, So if we know that the u function is 2y, 2 times of the y, and then we can compute the du dy, right? So the du dy will equal to the 2. Okay, so we can define the theta rate along the z rotation axis is the minus 1. Because there is 1/2 and multiply the dy, du dy. And the unit in here is the angle. So this is the radius per second. Okay. So right now we have the minus 1 radius per second theta rate. So the seconds, our target is, can we determine the delta t? Can we determine the delta t? Okay. So as we know that the distance, so we have the distance is the 1 centimeter, the travel distance. So you can see there is a travel distance. So if we can know that the travel velocity, so the u at the point location is 0.5 centimeter, we can know what the velocity at this point. So as we have the u functions in here, is 2 times of the y. So the 2 multiply 0.5. And we know that the velocity is the 1 centimeter per second. At the point locations is 0.5 centimeters. So this is the travel velocity. So we can know that the travel time delta t will equal to the distance divided the u, right? Because the u is the travel velocity and the d is the distance. So we know that the delta t will equal to 1 second. Only the 1 second. So finally, how can we compute the theta? The theta is equal to the theta rate along the z directions multiply delta t. Okay, so the theta rate is the minus 1 radius divided the seconds, and we only travel the 1 second times. So the rotation angle is equal to the 1 minus 1 radius. Okay, so that's our final answers. If at the location of 0.5 centimeters, and when the travel distance is 1 centimeter, the fluid particle will rotate the minus 1 radius. So do you know what the reason there is the minus? Because the rotation angle is clockwise, right? So you, by your right hand, is a minus negative rotation angle. Okay, and you can convert the radius to the degree. Okay, so we actually know the minus 1 radius. If we know that the radius pi, so 3.14 is the pi, is equal to the 180 degree, right? So you can convert the radius to be the angle. Okay, so you use your calculator to compute the rotation angle will cross about the 57.3 degree. So you can convert the radius to the degree angle and then the minus. Okay, so almost the 57 degree rotate clockwise angle when the point at the 0.5 centimeter and the travel with the 1 centimeter distance. Okay, so this is a very good exercise we can practice. The first exercise, we know how can we define the flow is rotational or not. So in case for this exercise, we compute the vorticity equals 0. So we can conclude that the flow is irrotational flow. And the second, for the Coulter flow, we actually know the flow is rotational flow. So that we will have the theta rate. So as you can see, the theta rate in here is not equal 0. So we conclude that the Coulter flow is rotational flow. And then we wondering to know the rotational flow, how the rotational angle during the different conditions. Okay? And then we can compute the rotation angle is equal to the -1 radius. And the rotation direction is the clockwise directions. Okay. So this is the exercise is correlated to the rotational flow. Okay, so in the following slide, I wondering to teach you how the difference Bernoulli equations for irrotational flow and the rotational flow. So we wondering to know the Bernoulli equation, how can we apply to the irrotational flow? And the next slide is the rotational flow. So how difference between the how difference in Bernoulli equation if we consider the flow is rotational or irrotational. So you will see the result. Okay, maybe we start here and have a break, and when we back, I will introduce